Hi everyone. IoT devices can apply levels of intelligence that previously we could only rely on humans to do. Today we're going to talk about IoT devices that spread and connect the digital world to the analog one, to the real world. And I'm going to talk about edge devices. And I don't mean CloudFront edge locations as an AWS service. I mean edge devices which are a compute capability that could be in disparate locations all around the world, potentially in their thousands or millions, and a compute capability that can operate autonomously without necessarily needing a connection to the cloud. And we're going to see how combining the latest in AI, IoT, and edge compute, what things we can build. So the agenda for today is I'm going to quickly go over the AWS DeepLens, and I think through a few sessions. You may already be familiar with that. We're going to talk about SageMaker and Greengrass, which are services that power the DeepLens. We're going to briefly touch on building and training a model using SageMaker, but I know there have been other sessions that spoke about that. We're going to deploy an AI model and inference code using AWS Greengrass, and of course there's going to be some demos. So what happens when you combine cutting-edge AI and IoT and an edge compute device? Well, we thought this would be a pretty good idea, and it's primarily a device aimed at developers. It has an Intel Core, Intel Atom CPU. It's got 8 gigs of RAM. It's got a GPU on board that's really, really good at processing AI models. It's not probably going to run the Crysis gaming engine as well as it probably could, but you know, for a piece of hardware that's reasonably portable, it's got quite a lot of tech in it. And one of the advantages is if you open this up and you power it up and you throw in your AWS account details, you should really be able to get going with a demo with a pre-trained model in about 10 minutes, which is pretty cool. And it comes with a whole bunch of sample projects. And for those of you who are in the keynote this morning, you may be familiar with the hot dog, not hot dog demo. There's some pretty cool stuff, like this artistic style transfer is trained from a whole bunch of photos of a place and compared to a painting done by an artist. And so the model actually understands, hey, from this picture that I see, how would an artist paint that? And you can do people and face detection and all that sort of stuff. Can we cut to the demo, please? So this is a DeepLens running a face detection algorithm, and it's a little bit delayed because I'm running the video over Ethernet, and I understand the irony of having an edge device hardwired via Ethernet, but for all the people in the room, I didn't trust that Wi-Fi would be able to saturate it. So this is one of the out-of-the-box features that you can just click and deploy in DeepLens, and you can do some face recognition. Now you can take that crop and then send it to a more powerful service and work out, if the person's smiling, or do some sentiment, or do person tracking, all kinds of stuff. But that's, really you can get going very quickly. Back to the slides, please. So it's really cool to do hot dog, not hot dog. But, the whole idea of hot dog, not hot dog was a TV show that was showing a completely pointless app. So it's really fun to see the capabilities of the device. But when I look at this piece of hardware, I see a whole bunch of problems out in remote locations and all kinds of areas where you can start to think about solving a problem differently. And one thing that deep neural networks are good at doing is this thing called feature extraction, where it's pretty easy to write a program to recognize the color of an apple or an orange and say, yeah, that's an apple. But if you're trying to write a piece of code that says this apple is ripe, this orange has some disease, actually find something meaningful about it, it becomes much harder. And these new types of machine learning are very good at learning by example, similar to the way a person does. So you don't have to program what a disease looks like. You just show it thousands of examples of diseased fruit, and it learns how to, work out the difference. And it's not just problems that are remote in terms of, being on a farm or something, but also think about data privacy and places where you can apply machine learning to data without actually having to send it anywhere. Not only is that maybe interesting from a medical point of view, but if you go to an oil rig, the first thing that the IT folks will tell you is that there's no way that you'll be able to stream 72 different video cameras of imagery off an oil rig over a tiny little satellite link. So there's lots of reasons why this concept of applying the intelligence to the edge really makes sense. And it makes you think, what does the future of compute look like? Is it this sort of grid and mesh of interconnected devices, none of which are particularly powerful unto themselves, but perhaps are able to really make operational decisions based by themselves? And if you can see the sign on that top left-hand side of the slide, that's kind of why I've got some of these out for my demo. I work a lot with mining and heavy industrial customers, and we were thinking about how a person tells that they're in a particular location in an underground mine. And it's pretty obvious. The person knows where they're driving, they know the location, they just recognize it. And as well, there's some cues that a human can pick up, like this sign. Lots of companies try to do underground sort of GPS location by using RFID tags, and there's lots of technological solutions. But what happens if you could apply something really, really simple, instead of a new piece of technology, start to realize where you are using the same sort of visual cues that a person would? So hold that thought, because we're going to come back to it later. In this DeepLens is a system called Greengrass. Greengrass can run on any device that will run Linux, basically. And it gives you a whole bunch of things that you would normally expect in the cloud. It gives you local compute capability. It gives you ability to send messages, not just to the cloud, but to other devices that may not be connected to the internet. It gives you an ability to store data and cache that, forward it to other systems, or forward it to the internet once Wi-Fi reception comes past once a week. And of course, it's secure. And the idea behind Greengrass is that you bake it into your equipment at manufacture. And on the DeepLens, which is running an Ubuntu operating system, the Greengrass runtime is just a Debian package that's installed. And when you write code for it, you're just writing a Lambda function, just like you would be running on the cloud, except the DeepLens provides a containered environment in order to run your code. So it's pretty cool. You can sort of write and test your code in the cloud and deploy it to an edge device. And another component that's pretty important, it doesn't run on the device, is SageMaker. Now, there's a whole bunch of steps in the data science process to build a model. And I used SageMaker to build this, and I still found it a bit of a struggle because I didn't really know what I was doing. And this is one of the really cool things about SageMaker is it's one of those things that is starting to make AI more accessible to people with developer sort of backgrounds like myself. And one of the things that SageMaker is really good at is this hyperparameter optimization. So that means, how many training cycles do I run through? How deep do I make my neural network? What's the architecture? Most of this is a black art. And so having SageMaker help optimize the parameters that to be honest, I don't completely understand, and the result is a much better model, that's really great. SageMaker also has this capability to deploy a model to an HTTP endpoint in the cloud, so you can give it, an image and it'll tell you that there's a hot dog in it. And we are not going to use that at all today because that's not the point of the DeepLens. Instead, SageMaker actually integrates with AWS Greengrass ML inference. So just like Greengrass will deploy a Lambda function onto your device and run on the same on the device as it would in the cloud, Greengrass ML inference does that for your AI models. That means that the face detection and the object recognition is actually happening on the device. And let me tell you just a little bit about collecting data. So when I was trying to build this project, it wasn't necessarily the first thing that came to my mind. And when you start to think about a problem that you might like to solve using this technique, the most important thing you have to start off with is, how am I going to get a data set? The algorithms are largely commoditized. Many of them are open source, and they're getting better every day. The data is the real competitive advantage, and that's what you really have to start from. A good example of that is driverless cars. Machine learning is really good at generalizing what it sees, but if it's never seen a white road because it's covered in snow, it doesn't really know what to do. So the more data you can collect, the better your model is going to be. And my model only has about 200 examples, so it's not all that great, but I'm going to show you an example of how that works. So you build and train a model using SageMaker, and that includes sort of creating a notebook instance, importing your data, training a model, and I'll show you a little bit of this. There's a great getting started guide on GitHub that we ran as a reInvent workshop for building your own model on the DeepLens. And just getting a little bit more techie here, when we're talking about the kind of models that you can run really easily on the DeepLens, MXNet models work really, really seamlessly, and these are the layers that you can support in MXNet. Part of the reason is that the model gets optimized into something that the Intel GPU understands, and these are the ones that sort of have a hardware mapping. Now, if that's a little bit too much for you, these are the layers that you need to build image classification networks and single-shot detection models. So SSDs are the ones that draw the boxes around the things that you see, like I'll be demoing, whereas a classification algorithm will say, hey, I know there's a hot dog in this image. I don't know where, but there's definitely a hot dog. So the next step is, once you've got a model, is that you need to go and deploy that model and the inference code using Greengrass. So this is just a little screenshot of what the DeepLens console looks like, a little summary of what your devices look like. And you go into a project, and it's as simple as you have a Lambda function that runs over the model, and you have a model. The model is the AI model that detects the thing that you want to go and find. And you can import a model from S3, and you can import it directly from SageMaker. So let's just recap very quickly about how all of this is working. You've got a DeepLens device, or could be a Raspberry Pi with a camera, that's pulling in an image. That image is grabbed by the Lambda function, and the Lambda function pushes that image through the model, and the model says, hey, I can see something in this image. And then the Lambda function can do something like make a visual output of that, or publish it to a MQTT topic, which is the message queue telemetry transport protocol that our IoT service uses. And that's what Greengrass devices use to talk to each other even when they're off the network. So I'm going to quickly go through how a Greengrass Lambda function operates on the DeepLens device. This is just one of the absolute standard templates that comes when you get started, so there's nothing super special about it, and you'll be able to see it and download it off GitHub as well. So you need to sort of create a Greengrass SDK client that allows you to sort of publish stuff to and from the IoT service. And this will sort of show a really easy way of publishing what the Lambda function sees. And then you need to create a separate thread. So this is running in a separate thread in the same function that is updating what the model sees and sends it out to a video feed. So that's what my video demo used earlier. You don't really have to do it, but it's really nice for a demo purpose because you can see what the thing is seeing visually, and humans like that. The reality is, if you're productionizing it, you probably wouldn't, because the whole point of the thing is that you're turning this analog video data into something more meaningful, like a number or how many hot dogs you can see, or whether you can see a location sign. And so you've got that function that's spinning really hot, that's sending out what it sees, and then you've got this inference function. So the inference function is also running on a tight loop. So unlike most Lambda functions that run as an event-driven model, this Lambda function is running hot. And the reason is it's trying to pick up and run the model at as many frames per second as it can, so it can tell you what it sees. So this is literally an infinite loop. It loads up a model, and it tells the DeepLens to run it on the GPU, because you know some models actually do run nicely on a CPU, and then it starts publishing that information. And this is the part where you know the top bit, the get last frame, that is literally getting an image from the camera to say, I've got an image, and the bottom line, the model.do inference, is running the image through the model and getting a result back out. So just to recap, you've got an image coming in from the camera, it's loaded up by the Lambda function, pushed through the model, and then you've got some sort of output. And that output could be over MQTT. So you can see there's a publish, almost down the bottom of this, there's a publish IoT topic and a payload, and that's going to look like this. I can see a chair, I can see a person, I can see a TV monitor, and the degree of certainty to which you can see it. But you can also, publish that visually. So you can see the first bit of this function is actually drawing boxes, and that lets you do this. So it goes, I can see a chair, and I can see a person, and I can see a TV monitor, and this is actually where they are, which makes for much nicer demos. One quick tip about optimizing your model is that even though the model is written in MXNet and hosted on SageMaker as an MXNet model, if you include this line, it's a one-line call, which is pretty handy because there's a lot of other things about this which aren't all so easy. This literally pulls the MXNet model and optimizes it on the device for the Intel hardware, just in one line. So it's kind of handy when you think, if you've got a model that's operating in MXNet world in SageMaker, you can go and run the same model on your edge device without having to sort of write code to change the type of model in the way that it runs. So I might just cut back to the demo screen. Actually, hold off for a tick, and I'll just set it up. Okay, can we cut over to the demo, please? So this is how I built my model. I went around my office and I took a whole bunch of photos of people, and then I tagged the image in, and that was kind of handy. And then I realized I could save time by like putting heaps of the signs in one place, and that would give me like more training data, and I'm pretty lazy, so I started doing that. And I wanted to generalize, and then my dog, and there's a reason that it looked like that, because I was actually started to train it on this, which is part of the demo. I started sort of just doing some screenshots to work out if, you know, from this perspective, if I could collect more data around this recognition of, you know, of a location sign. So these signs are sort of my version of that earlier slide where you've got like this underground mine location. So in order to build that model, I've used something very, very vanilla out of the MXNet incubator GitHub repo. It's called SSD, Single Shot Multi-Box Object Detector. It's actually potentially not even the latest way to find objects and draw boxes around them, but it works pretty nicely. So it comes with some demos on how to build a model. And there's a lot of training data. So it comes with data sets that let you sort of train the model without having to go and collect it. So one of the challenges for me was getting all of my data of those tags that I'd taken and then putting it in a format so that I can actually run training myself on it. And I just thought I'd quickly show you the DeepLens console deploy. So you go into this, you know, DeepLens, you've got a project, you can go and click on it, click deploy to device. It'll give you your devices, you hit review, and it'll deploy it. And it's actually using, Greengrass is using its own channel of communication over MQTT to say, hey, hey DeepLens, I've got a new model for you, and I've got a new bit of Lambda, download them from S3, and then go and start running them. I'm not going to do that because I've actually got it running already. So I'm going to move this over onto here. And it runs quite nicely off a battery pack as well, which is handy for making it portable. And the demo actually also runs pretty nicely off Wi-Fi. So when I was running at home, even streaming quite a stupid amount of video for diagnostics, it worked really quite nicely just over Wi-Fi, but I'm a little bit paranoid about bandwidth in this area. So apologies that this will be dragging a cable behind it. So I'm just going to fire up the visual output of this, and with any luck, we'll have the sign detected. So I'll just show you what programming, what I'm doing. It's literally just calling mPlayer. mPlayer is going to open a moving JPEG picture stream and display that. And there you go. So the model can actually see this sign here, and it's quite certain that it is a sign that I've trained it on. And this is, I love my job. And you can see there's a little bit of lag. It's funny, the actual MQTT output is much more up to date. And you can see it's really interesting. Because I don't have enough data, it's finding some other stuff that look in no way like a sign and assigning that to it. So it's a really good example of, you know, how probably not to build a model. But you can also see, you know, it's pretty certain as well. There's like 80% certain that's a sign. So, and you know, you could just move the camera just a little bit, and we'll see that catches up. Yeah, it's really liking that. It's funny, like, because it doesn't have a huge amount of data, as it moves over, like, you could move it completely, you know, insignificant distance, and suddenly it can detect something from 50 to 100. So this is a really MVP kind of demo, but you can see this device is now able to go and say, look, I understand what this particular sign looks like from only, I think 150 examples, so which is pretty good. So it's got that one too. So I'll drive it back, full power. And I was just going to show you, like, it does have a pretty good ability to generalize. So the model was trained from all of these signs, but I'm going to put this one here. I didn't test this earlier, so I hope it works. And this is a sign that I did not train at all. So this sign, the model has never seen, and yet it's still like 90-something% certain that that is a sign. And that's because the model has learned, like, from enough data that a sign kind of looks like this white thing with some 2 lines of black blobby on it, and I think that this is a sign. So that's kind of cool, but just because it can detect the sign doesn't really help all that much. So what happens if you start to take that another layer, 3.10, and actually go, hey, well, I can crop where a sign is, and so what can I do? Maybe we can OCR that. So this is using Tesseract, which is completely not designed to do this. Tesseract is an open source OCR engine. It started off invented by HP using old school sort of technology, and now it's developed using deep learning as well, but it's really designed to just read books. So, but you know what? It's good enough to go and say, hey, I can recognize that this sign, because it's been cropped by the first algorithm, says 2, 3, 4, 5 EFG. And hey, I preset where I would put these signs, so I can map that out on a camera to show my location. So suddenly this device, all by itself, is actually working out where it is. And I can probably do an example of it not working pretty well as well, because it's OCR, if it's on a funny angle, it doesn't really, like, oh, that's worked. Okay, so we've seen that it's moved over, and we've updated the truck on the map. This is my version of a map, and we should see it update. There we go, we've got the signs up in the clouds again. And there we go, 3, 4, 5, 6 ABC. And let's be brave, and I'll try and finish that same one. It's actually kind of more important that it, oh, there you go. So it's on a bit of a slant. So you can see the latest crop, it's gone unknown. Just because the text is in a funny spot. So this is where I say it's a little flaky. If I drive it a little bit again, it'll get a different crop of it, and it can go and do the OCR from there. So can we cut back to the slides, please? So I guess I was really trying to show using this tech to solve real-world problems. I know it's a bit of a stretch to imagine, but once you've cropped those signs, you've actually got a data collection service. So you could start to, dump the crops of the signs to disk, buffer and upload them later when they're really, they're really small files, and you can add that to your training set. So you could do something like build a proper classification network that takes the signs and then actually determines the location. And this is something that is tolerant to putting the camera in behind a dirty windscreen. They're really, really good at generalizing. So it's a very, very different type of tech. And when you walk out of the room, I want you to think about, it's cool to do this on one device, but what kind of problems can you solve where you need human sort of style attention to solve the problem, but you can deploy it in tens of thousands or hundreds of thousands of devices. And I think it's really interesting to see that this kind of software is making its way into general purpose software all over the place, and you may not even realize it yet. So I know mining companies, some mining software companies that I'm talking to don't have this idea, but have a whole bunch of other ones around turning the analog world, an image or a sound, into something digital that's really meaningful and can actually drive value for your business. Thank you very much for your time, and have a great afternoon. Cheers.